Good morning. Let's get started here. You need to go bother Daddy about it. Can you please close that door? So we left off, we had been talking about how long a rattlesnake is. And I showed you two different ways to solve it when you're within the metric system, right? So if you're in the metric system, you can either use dimensional analysis or you can use like King Henry died before drinking chocolate milk, which some people find I like that way. It's a little faster. I don't even have to like write it out to do the hops. We did a multi-step per here. You did one here, how many seconds are in weeks. So we did this nice long chain together one. So you can keep, chaining all those together till you get to the unit you want. So in the slides, come on, too many things open. All right. So using two or more conversion factors, we've already talked about this, so you can link them together. Here we've got one where it says a doctor's order prescribed a dosage of 0.150 milligrams of Synthroid. If tablets are in stock, contain 75 micrograms, that's the MC is for the micro. How many tablets are required to provide the prescribed medication? So we need 0.150 milligrams. Each tablet has 75 micrograms. So we need to do a couple things. We need to take our milligram value, we need to convert it into micrograms, and then we can use this conversion factor, which is how much medicine is in each tablet, right? So 1 milligram has 1,000 micrograms. That's that first step. We start with how much we need. We convert it to micrograms. And then we know for every one tablet, we are going to get 75 micrograms. So the micrograms will cancel and we'll be left with just the unit of the tablet. And it says we need 2 tablets to fulfill whatever this order is. So there was a multi-stepper. We did something similar to this, so we don't need to go through that. Here, you guys work on this one. So if your pace on a treadmill is 65 meters per minute, how many minutes will it take for you to walk a distance of 7.5 kilometers? And I want you to try and set this up using dimensional analysis, okay? Little assistance here. This is really the given piece of information, given. And 65 meters per minute, this is behaving as your conversion factor for this given problem, right? If you were maybe faster, you were running, this number might be bigger, but for this specific problem, you're going 65 meters per minute. So I'll have you guys give you 3 minutes or so to set that up, state your given, state what you're trying to find, and come up with that.
You're muted, Ms. Henderson.
Yeah, I'm muted because I'm letting you guys work on the problem for a couple minutes. Yeah. Okay. So for this problem, given piece of information is that we know we went 7.5 kilometers. We're trying to find minutes. So we need to relate kilometers and minutes. I don't have anything that's directly kilometers to minutes. I do have meters to minutes though, right? So I do have a conversion factor that says I go 65 meters in every 1 minute. So this is my conversion factor. This thing though is not quite where I need it to be. So my first step is going to be to go from kilometers into meters. That is just using a shift and prefix. And then from meters, I can go into minutes using the given conversion factor for this problem. So I have 7.5 kilometers. I'm going to set up in dimensional analysis, but you could use King Henry died before drinking chocolate milk. So for every 1 kilometer, there is 1,000 meters. Right, kilometers will cancel. Then I'm going to use this relationship. So if meters is on the top here, I want meter to go on the bottom. And then I want minute to go on the top. And I just fill in the appropriate numbers. So 65 for meters, and that's in every 1 minute. Remember when it says per something, you just put an inferred 1 on the bottom unit. The number sticks to the top unit. So meters will cancel and we end up taking this 7.5, we're gonna multiply it by 1,000 and we're gonna divide it by 65 and we'll be left with just units of minute. I'm gonna clear this out. Sorry, go over to the slides. Sometimes I don't like how the slides write things. So here's what we had going on here. They wrote it 1 kilometer is equal to 10 to the 3rd meters. Don't get freaked out when you see things like this. 10 to the 3rd is the same thing as 1,000. right? One with 3 zeros. So we should get 120 minutes honoring 2 sig figs. So sometimes within a given problem, you'll be given like a conversion factor. Same thing with that last problem, the conversion factor for the pill dosage was that each tablet, one tablet is equal to 75 micrograms. So we can see here one tablet, 75 micrograms. If this was a different problem, if it was a different medication, that number could change, right? So you've got to be able to pull out conversion factors for a given problem. All right, so I'm going to give you, I want to give you one more problem, a conversion factor problem. What do I want to do here? Let's see. Trackpad is messing up. Natalie's saying, for the previous question, would it be acceptable to first convert the 65 meters into kilometers, then use the number in the equation? You could, but I would avoid converting within your conversion factor because that was 65 kilometers per minute. So then you're converting, yeah, I would stay away from converting conversion factors. I would convert the given information. Doesn't mean you can't do that, but it can get a little squirrely if you're like leaving off units in conversion factors or not converting them properly. Okay, how much does it cost to drive 650, I'm gonna say kilometers, if gas costs, I don't know, what does it cost now? Is it like just over $2? Something like that? Okay, we'll say $2.19 per gallon. Or hold on. How much does it cost to drive 65 kilometers if gas costs $2.9 per gallon? And your car gets 25 miles to the gallon. Okay. How much does it cost to drive 650 kilometers if gas costs $2.19 per gallon and your car gets 25 miles to the gallon? So I want you to set this up in dimensional analysis. This is a multi-step problem, so there's more than one conversion factor you'll need. Okay, so this problem is multi-step. There's a couple things going on. So our given piece of information is that we drove 650 kilometers. So that will be what we're starting with. Given that I have 650 kilometers, I'm trying to find something about money, right? How much did it cost? So I've got two conversion factors here. One says that it costs $2.19 for every 1 gallon. That's one thing. And I also have this thing that says my car gets 25 miles to the gallon for every 1 gallon. All right, so I've got a distance, I've got a relationship between distance and gallon, and I've got a relationship between gallon and money. So I can start figuring out how I'm going to leapfrog here. Now this is in kilometers, this thing is in miles. So I'm going to convert kilometers into miles first. So the first thing is kilometers, we're going to go to miles. Then from miles, I can get into gallons. Then from gallons, I can get into money. And then it's just really a matter of sticking the right conversion factors in the right spots. So to go from kilometers to miles, this is the relationship that 1 mile is equivalent to one. I don't know this one off the top of my head. I have it somewhere. 1.609, 1.609 kilometers. If you use the relationship where you say 1 kilometer is equal to 0.62 mile, that's fine as well. To go from miles into gallons, this is going to be this guy here. So I know that I get 25 miles out of every 1 gallon. And then this step here, gallons to money, well, it is $2.19 for every 1 gallon. So we're going to string these together. Start with our given piece of information, which says, hey, we get 650 kilometers. I want to go to miles. So if kilometer is on the top here, I need to put kilometer on the bottom here, and then I put the mile on the top. As far as the numbers, this is 1.609, and this is for every 1 mile. The next step is to go from miles into gallons. So I need to relate mile to gallon. And for my specific car, I get 25 miles in every 1 gallon. The final step is to relate gallons. I'm going to put gallon here so it cancels with money. All right, and every 1 gallon costs, let's move that dollar over, dollar sign over. It costs us $2.19. $2.19. So kilometers are going to cancel out. Miles are going to cancel out. Gallons are going to cancel out, and we should just be left with units of money, dollars. This process here of like how I set up this flow chart, this is critical thinking, okay? This is something that I can't really give to you because every problem is going to be slightly different. There's not like, oh, well, I memorized how to do this problem, so now I know how to do every problem. That isn't how it's going to work. It's going to take a little bit of time for you to go from a word problem into, you know, your appropriate flow chart. And that's just going to be practice. All right. The more you practice doing these, the more homework assignments you do, additional worksheets you do, the better you're going to get with these. All right. I got to plug it into the calculator. Sorry. Give me just a second. So multiply anything that's on the top, divide anything that's on the bottom. So I've got 650. I'm going to multiply it by that 2.19 all the way at the end. I'm going to divide it by 1.609, and I'm going to equal it out, and then I'm going to divide it by 25. So when you're plugging this into your calculator, you want to take, you know, your number, you want to divide it by this thing, hit equal and then divide it by this thing, or you can sort of chain them together. So at the end of it, I got, I'm gonna do 3 sig figs, $35 and 40 cents. Okay, so wasn't that much. 650 kilometers. I mean, you kind of want to cut that in half to get how many miles that is. It's like 350 miles. So yeah, that makes sense. How did you get 1.609 kilometers? I got that from the internet because that's the relationship between those two. All right. I think your lab manual has a conversion factor sheet, LJ, that you can use in your textbook as well. When in doubt, I go online to find some conversion factors. I just make sure I'm getting it from a good source. Cecilia, what would be our sig fig for this problem? It would be, actually, it wouldn't be 3 sig figs, it would be 2 sig figs, because my given piece of information up at the top there is only 2 significant figures, right? 650, my bad. So it should just be $35. We would round this, the 4 would tell the 5 to, it's not even a 4, it's a 3 actually. So I'm gonna round this to an even $35. Thanks for pointing that out. Any other questions on that? So sometimes conversion factors are given to you within the problem. Like these are specific to this problem. Sometimes conversion factors are something you have to look up, right? So kilometers to miles, I had to find that. That doesn't change, right? The relationship between kilometer and mile, no matter what the parameters of this problem, that is a standard conversion factor. These things, this 25 miles to the gallon or $2.19 per gallon, that could change depending on how good you are at driving or what the price is of gas for that day. All right, so we've got one more concept that I want to go over for chapter 2, and that is density. So looking at this is a beaker filled with water. Water has a density of 1 gram per milliliter. That's where the gram per milliliter comes from. Then we've got ice, which is actually slightly less dense than water. Water and ice are one of the few things that when you move it into solid form, it becomes less dense. Usually as you move into solid form, you become more dense, but ice doesn't do that. So ice will float. Cork is much less dense than water, so it's like sitting right at the surface. Aluminum is more dense, so it's going to sink, and then lead is much more dense, so it sits right at the bottom. So density, if you look, these units, they're 2 units. There's a mass value and there's a volume value. So it's not enough to talk about density as a weight thing. Oh, something that's more dense is heavier. It's not necessarily that it's heavier for a specific volume, right? You've got more material, more mass in a given volume if it's more dense. So here are some of the densities we've got, again, so we've got things that are less dense than water, and we've got things that are more dense than water. We've got some densities of liquids. In general, liquids tend to be less dense than solids, but not always. We look at mercury. Mercury is a very dense material and it's liquid. And then we've got gases here. Gases usually are less dense than water, but there are some instances where we have a little bit more density. So let's talk about the equation for density. Density equals mass over volume. So if you want to solve for density, you need to have 2 pieces of information. You need to have its mass and you need to have the amount of space it occupies, which is its volume. There's a bunch of different units for density. It will always be a double unit. It'll be a mass thing over a volume thing. So density for liquids and solids a lot of times tend to be in grams per centimeter cubed or grams per milliliter. Remember that a centimeter cubed or a cc is the same thing as a milliliter. That's a one-to-one relationship. So this unit and this unit are actually talking about the same amount of density. Density for gases, a lot of times they'll give those in grams per liter because they have such a low density. It doesn't make sense to talk about them in milliliters. You'd have such a small amount in that small volume. So they stretch it out to a liter. There are other ways that we could write density though, just FYI. I mean, we're not going to see these quite so often, but you could write it in, you could write it in kilograms per milliliter. You could write it in centigrams per foot cubed. I don't know why you would write that, but that is a possibility, right? There's some sort of mass over some sort of volume. So how do we get mass? Mass is usually pretty easy to find. We just stick it on a scale. Okay, so this bar here, I put it on a scale and I'd use the mass 68.60. So let's say that this is our mass for the object. If I want to find the volume of an object, specifically the volume of an irregular object, a lot of times we find that by doing this process called displacement. So you take like a graduated cylinder, so one of these thingies, and we fill it with liquid, okay? And then I take whatever the irregular object is and I stick it in there. And initially this is at a volume of 35.5 milliliters. When I stick the object in there, the overall water raises to 45 milliliters. That change in volume of your liquid is the volume of the object. Think about it like if you were to fill your bathtub up all the way to the top and then you get in, what would happen? A bunch of water would spill out because your space, the space that your body occupies, displaces the liquid. So that's a good way for us to get the volume of an object. So in this case, we said to find the volume of the object, you find the difference between the final volume and the initial volume of the liquid. So in this case, there was a change of 9.5 milliliters. We could directly change that or convert it to 9.5 centimeters cubed, because remember, these two units are equivalent to each other. So in order to find the density, if we wanted to find it in grams per centimeter cubed, we would take the density of our object, or I'm sorry, we would take the mass of our object, which is given to us from a scale. We would divide it by its volume, and we'd end up with 7.2 grams per centimeter cubed, which seems like an appropriate amount for, what is this, zinc? It seems like an appropriate amount for density. It's not enough just to have the mass. You've got to have the space it occupies as well. So go ahead and solve the density for this one. So this says, what is the density in grams per centimeter cubed of a 48.0 gram sample of metal? If the level of water in a graduated cylinder, it rises from 25 milliliters to 33 milliliters after the metal is added. So I'll give you all 3 minutes for that one, 2-3 minutes. Okay, so we're trying to find density. Now, when solving for density, it's not really a dimensional analysis problem. There isn't like a conversion factor. It's just an equation. So we've got, density equals mass over volume. We want to find this, so we need this and we need this. My mass is given to me right here, 48.0 grams. So I can put that 48.0 grams. My volume, I have to calculate that, right? So I need to take 33 and subtract 25, which would give us what, 5, 6, 7, 8, 8.0. I'm going to use 0.0 because we're subtracting, so 8.0, and the units are milliliters. So this divided by this, it should give us a value of what, 6 grams per milliliter. It wants it in grams per centimeter cubed. Okay, milliliter and centimeter cubed are the same unit, so you could just swap that out for centimeter cubed. So sometimes you can be given density instead of being given like mass and volume, you're given density and mass, and you solve for volume. These slides are going to guide us into using density as a conversion factor, because look at density. Like this thing over here, we've got 6 grams per milliliter, 6.0 grams in every 1 milliliter. So if this is density, well, density is a double unit, right? It's 1 unit over another unit. So this can be a conversion factor. I will teach you that way, and also just plugging and chugging it into the equation, which I actually find easier. So state the given, write a way to calculate it, use equalities with the density as your conversion factor to go from starting to end. I don't really like that problem very much. Okay, so let's do this one. An unknown liquid has a density of 1.32 grams per milliliter. What is the volume of a 14.7 gram sample of the liquid? I'm gonna walk you guys through this in 2 separate ways. So go ahead and write the information down. We've got 1.32 grams per milliliter and 14.7 grams. 1.32 grams per milliliter and 14.7 grams. We're trying to find volume. So writing out my equation, density equals mass over volume. If I'm trying to find volume, I need to get volume by itself. So in order to get volume by itself, I'm going to move volume over to this side and take density and bring it over here. So I'm going to multiply this side by volume, multiply this side by volume, divide this side by density, divide this side by density. Volume cancels, density cancels, and we're left with volume is equal to mass divided by density. I just isolated for the variable. If you are not great with isolating variables, here's a little trick. Draw a triangle. I swear I can draw a triangle. Draw a triangle here. Okay, and we're going to divide it in half, and then take the lower part and divide that in half. In the lower left-hand corner, I want you to write a D for density. And in the upper, I want you to write M. And then in this lower right, write V. Okay, they've got to be in this order. So think of this bar as a divisor bar, divider. Think of this bar as a multiplier. You should be able to derive every equation you need off of that. So if I want to solve for density, density will equal mass divided by volume, right? If I want to solve for volume, volume will equal mass divided by density. And then if I want to find mass, it's going to be density times volume. And so you can get all the things you need off of that. If you're pretty good with isolating variables, you can ignore that and just rearrange as needed. So we've got this equation here that tells us volume is equal to mass divided by density. Make sure your units are the same. So this is grams and this is grams. If this happened to have been in kilograms, you would want to convert from kilograms to grams because you can't plug those in together if the units are different. But this one was relatively easy. So we're just going to plug and chug. So volume equals my mass. Well, in this case, it's 14.7 grams divided by my density, which is 1.32 grams per milliliter. I always include my units because I get to watch them cancel out and I end up with the units that I just want. So in this case, gram and gram will cancel. And then I've got this unit of milliliter that's below a fraction bar and below a fraction bar. Anytime you divide something twice, divide by, it flips it back on top. So my unit for this thing is going to be the milliliter. So we just take our 14.7 and divide it by 1.32. And we end up with 11.1 milliliters. I like this best. I like to just rearrange the equation and plug and chug. The slides are going to show you how to use it in this dimensional analysis way though. So if we look at our density here, we've got this value that says density is equal to 1.32 grams per milliliter. That's a conversion factor. It's two units related to each other. It's like saying 1.32 grams in every 1 milliliter, or it's like saying 1 milliliter will yield 1.32 grams. Y'all seen how those look like conversion factors? Okay, so one way you can solve it is take your given information, which was our volume value. Here, this 14.7 grams. 14.7 grams, and then arrange it in dimensional analysis using the density as a conversion factor. So I don't want to use that one. I want to use this second one, right? Because I want grams to go away and I want milliliters to stay. So the 1.32 gram goes on the bottom, and that's for every 1 milliliter. The unit of gram will cancel and you'll be left with just units of milliliters. You're doing the same thing. You guys see how you're taking this and dividing it by density? In the top value, that's what we did, or the top situation, we did the same thing, right? We took 14.7 and divided it by the density. You're doing the same thing, it's just a slightly different setup. You'll get the same answer, 11.1 milliliters. I don't care which way you do it. You can either plug and chug, or you can do dimensional analysis. It's up to you. Don't do both of them. Pick one. So I don't know if the slides have another good example for density. I feel like not. One other thing I want to talk about, and then I'll give you another density problem, is maybe it doesn't. Is specific gravity. Okay, so specific gravity is the relationship between the density of a substance with the density of water. What is the density of water? It is 1 gram per milliliter. So you're just taking your number, your density, and you're dividing it by 1. What it does is it strips your value of its unit pretty much. So like if I have that 1.32 and I want to find its specific gravity. So we know density up here is density is equal to 1.32 grams per milliliter. And I want to find the specific gravity. Okay, specific gravity is taking your object density and dividing it by water's density. So you're taking this 1.32 grams per milliliter and you're just dividing it by what's the density of water? It's 1 gram per milliliter. All right, so you're not changing the number. It's still going to be 1.32. What happens? The units cancel. So it just becomes a unitless value. why would you use that? If you want to change units and things like that. We don't do a whole lot with specific gravity, but if you get a question on the homework or something like that, that's what you're doing. You're just taking it and dividing it by 1 to strip the unit. So let's do let's do another density problem. I'll type it. How much does, or how many grams? How many grams are in 16.2 liters of a liquid with a density of 1.87 grams per centimeter cubed. Okay, how many grams are in 16.2 liters of a liquid with a density of 1.87 grams per centimeter cubed? So I'll give you all about 3 minutes to work through that. It's a density problem. Okay, so the density problem. And sometimes when I have those, I'll just say density equals mass over volume. Trying to solve for grams. So gram is a mass value, so I want mass. So mass is going to equal density times my volume when I isolate that out. I've got some given information here. I'm given the volume. So I know volume equals 16.2 liters. I'm also given my density, which is 1.87 grams per centimeter cubed. So what happens sometimes is students will, they get like overzealous and they're like, all right, I'm just going to plug this into the equation. And they take their volume and they take their density and they stick it right in there. This is a good thing to, this is a good reason it's good to put your units, because if I take 16.2 liters, all right, and I multiply it to 1.87 grams per centimeter cubed, what I notice is, my units aren't canceling. This is a liter and this is a centimeter cubed. I can't cancel them to get my unit of gram. So I know that I've got to make sure first that I'm converting. So that's why I always carry over the units. Another thing you can do is when you're staring at your given information, make sure the units are lining up. This is in liters, this is in centimeters cubed. So I need to get liters to centimeter cubed. Well, the first thing I'm going to do there is get liters into milliliters. So move the decimal over 1, 2, 3 spots, or 16 to 00. So this is milliliters. And then remember, a milliliter and a centimeter cubed, or a cc, are the same unit. So this is equivalent to 16.200 centimeters cubed. Same thing. Right, this and this. Now I've got the same units. When I plug it into my equation, they should cancel. So I'm going to take, so mass equals my density, this 1.87 grams per centimeter cubed. And I'm going to multiply it by my volume, 200 centimeter cubed. I like that because the centimeter cubed is going to cancel. So as far as plugging it in, 1.87 times 6. I get 30,294 grams. I've got it. Would the milliliter not be 1620? I'll make sure I did that correct. So I have 16.2 liters. I want to convert this into milliliters. All right, King Henry died before drinking chocolate milk. I'm at my base unit. I want to get over here. I need to hop my decimal 1, 2, 3 spots to the right. 16.2, 1, 2, 3, fill it in with zeros. Does that make sense, Alex? Yes, no, maybe so. I'm waiting in the chat. Yeah, got it. Okay, good. So we end up with this number. We want to clean it up a little bit. We want to go with significant figures. So 3 significant figures. So the 3 I'm going to keep, the 0 I'm going to keep, and the 2 I'm going to keep. The 9 is going to tell the 2 to round up. So it'll be 30300 grams. You could write it in scientific notation as well, which would be 3.03 times 10 to the, 1, 2, 3, 4, 4, 10 to the 4th grams. Those are saying the same thing. You could have solved it in like dimensional analysis. You would have gotten the same thing. Okay, so I'll put it in dimensional analysis. Start with our given, which is this thing here. I have 16200 centimeters cubed. I use my density. I don't remember. 1.87. Okay. It's 1.87 grams for every 1 centimeter cubed. Those will cancel and we'll be left with just grams. right? And this number will be the same. It'll be 30300. We're doing the same thing. We're multiplying the two values. So I don't care how you solve it. Either way, just make sure you solve it correctly. Questions on density? Not too bad. Okay, so that is everything for chapter 2. Let's look at the syllabus together real quick so that we can be on the same page. Not too bad. Yeah, hopefully it's not too bad. My goal is to make things as accessible as possible, almost to the point of boredom. Like I almost want you to be like slightly bored because you're like, this isn't that bad. This is easy. But not so bored that you check it out. And I know it's chemistry, so that may happen from time to time. Okay. It's just so we're all on the same page. I won't always check over, but we'll do it for the first couple weeks. So we finished up chapter 2. We're good there. You've got some labs that you need to turn in by Sunday. Okay, so the first lab, chemistry and measurements, and the second lab on conversion factors. And then you also have your second mastering chemistry homework assignment. So hopefully you were able to get your first one done. Now you have mentally have access to everything in chapter 2. We've lectured on all of it. So you should be able to do that. Remember with your labs, you need to fill them out in the physical lab manual. You will take a picture of them and then you will submit them to me through the Moodle website. So let me show you where you will do that again. Reiterate it enough. Okay, so you'll submit your lab 1 here and you'll submit your lab 2 here. So once you've completed them in the physical book, you'll take a picture, convert it to a PDF, and then you'll submit them here. Please submit them on individual pages because I don't want to have to read like super tiny labs. All the lab procedures are here. So if you click on this, this will tell you how to get through each of the labs, what I want, what I don't want. So going through this, and it's got some additional videos for things that you can't perform on your own. One thing I want to talk about with the lab manual setup is that the procedures for the labs sit before the labs themselves. So if we go to, you've got your lab manual with you, go to page 19 on it. I had a student ask me this and I forgot since we're not meeting. I usually go over this. So for that first problem where it says rounding off, so you've got these numbers and there's a student that has rounded the numbers and you need to determine whether it's correct or not. And people are like, how many sig figs am I supposed to round? I don't know what I'm supposed to do. Okay. Well, for page 19, I want you to go back to page 15. And you'll see that it says experimental procedures. And it says A, rounding off. A student rounded off some numbers to 3 sig figs. So that's where it gives you the details on what you're supposed to do for the data sheet. Okay. So if you're ever not sure like what you're supposed to be doing off of the actual report sheet, go back a couple pages to the experimental procedure and there's some more information in there on how to run them. All right. Cool. So that's all I've got. If you've got any questions, feel free to ask anything you want to talk about as a group. Otherwise, if you have personal questions, hang around and I will bring you in from a waiting room one at a time. And it is Thursday, right? So it's like the weekend pretty much. So make sure you get your stuff done for Sunday and have a good weekend. I'll see you guys next week. Bye.
You said you wanted each page as a PDF.
Yeah.
The way I scan it on my printer, is that okay, or have you looked at it yet?
Yeah, if you've got a printer, scan it on there. That'll be great. Otherwise, you could, the reason I offer taking a picture with your phone is because a lot of people don't have a printer. So yeah, if you've got a scanner, just use that. That'll be the easiest way, I think.
Okay. And if
Okay.
you want to pass it on, I've got an HP 3-in-1 printer that I picked up at Walmart for 39 bucks.
Oh, that's not bad. Okay, cool. Yeah, and you'll use it in other classes. All right, Sarah, thank you.
Have a good weekend.
You too. Hey, Shelby, what's going on? You're muted, so, oh, there we go. No, still muted. Shelby, can you, yeah, you gotta unmute yourself. I can't hear you.
Sorry, I thought I pressed.
No, no worries.
So I scanned in my 2 labs, but it was my first time using the Cam Scanner app, so I put them all in. I did it all at once.
Okay,
Let
let me check.
Do I need?
Let me check and see how it looks.
Okay. Because I think it still has the option for me to take it out and like.
Yeah,
redo.
yeah, you can mess with it.
Okay.
No, that should be fine. Yeah.
Okay. Because
That should
for
work.
the second, I just
Should work fine. It looks like it are the software automatically puts it on separate pages for you.
Okay. Cool.
Okay.
Okay. Thank you.
All right. Any other questions?
No, that's all.
Okay. Have a good weekend.
Thanks, you too.